Today, the cross product. No concept I can think of in math is more mysterious at the start and more powerful at the end than this. So as I go through this, if there's moments where you feel confused, that's okay, actually, in this lesson. Just let it develop, let the ideas of cross product get through, and then as you're doing homework, you'll see some of the power of this, but more of the power will come through when we do some applications. So there's another way to multiply two vectors. We've seen dot product. One way to multiply two vectors is to dot product them, and that's finding out how much one vector pulls in the direction of the other vector. The other way to multiply them is cross product. And to totally give it away at the start, what cross product means is how much one vector is twisting the other vector. So we've got pulling and now we've got twisting. The applications to engineering are looming here. So earlier we became familiar with the dot product. A type of vector multiplication that results in a scalar. So the answer was a number, like a 2 or a 7 or a 5.2, or negative numbers as well. It could come out of that. And at this point, we'll introduce another type of vector multiplication that is called the cross product, which has numerous applications in geometry and physics. Unlike the dot product, the cross product results in a vector quantity. So let's get our highlighter out for that. Going to get a vector as the answer here when we multiply the vectors as a cross product. So here's how we define the cross product, and this is sort of strange how this goes, is we start with a definition of it, and then later on we start to see why the definition is what it is. So have faith that the definition has been chosen carefully so that it is a powerful way to do this. So the cross product, u cross v of two vectors, u and v, is a vector with magnitude. Okay, that's important. There's going to be two steps defining cross product. One is first find out how big it is, what magnitude it has, what size it has. And to do that, we go magnitude of u, magnitude of v, sine theta. Almost as simple as dot product to find the magnitude. And where theta is the angle between u and v when arranged tail to tail. U and v acts perpendicular to both u and v in a direction given by the right-hand rule. Now, I'll try and explain it here, but I've posted another video about the right-hand rule so you can try and see it as well, because sometimes the explanation I'm going to give here is something you really have to see, and I've posted another nice video there to show this. The way to understand the direction that the cross product acts is it always acts perpendicular to u and v. So when you're doing the cross product with two vectors, u and v, your cross product will always be perpendicular. Now picture u and v laying on your desk or the table you're sitting at. If u and v are both in that plane, then u cross v is going to stick straight out of the plane, either upwards or downwards, either towards your face or down away from your face. And which direction is it? Well, it's decided by the right-hand rule. You put your fingers along the first vector, u, in such a way that your fingers, when you close your fist, the fingers wrap towards v. So when it wraps towards v, your thumb points in the direction of u cross v. There's only one way to do this, using an acute angle. So you're not going to be going backwards to get to v. So in the picture there, the hand actually weirdly is in the right spot. It's saying, hey, if I put them along u and I could close my fingers towards v, then u cross v is straight up. Now, if that seems completely weird, watch that separate video, but if not, I'll try and explain it with these three examples that are down here. Here's a cross b. So imagine right now, take your right hand and put your fingers along a there. Now, there's two ways to do that. You could either put your fingers so that your palm is heading towards b, or you could put your fingers along a so your palm is away from b. The direction we want is so that your palm is towards the second vector. And so when you do that, you should see your thumb is pointing straight up towards you. So that u cross v, in this particular case, our a cross b, your thumb comes out of the page. Take a look at this one and try and put your fingers along a. If you put your fingers along a in this one, oops, put the fingers of your right hand along a here. If you put them so that your palm is sort of facing towards you, you see your fingers won't wrap towards B. We need them to wrap towards B. So you need to turn your hand over, and this is really difficult to do, but to put your fingers along A in such a way that the palm is towards B, and then you can wrap your fingers towards B, and you should see that your thumb points into the page, not out of the page. And this one's sort of a trick one because A and B are not tail to tail, so I'd have to extend B out like this, put my fingers along A here in such a way that my hand, my palm, can wrap towards the B vector right here. And if I do that, my thumb points up and that points outward. If that completely boggles your mind, you can try rewatching it again, or watch the separate video, because the separate video really shows it with a hand on the screen there. Can you think of any real-world scenarios where two vectors would act like that, and what you'd get is something moving in or out? And this is all about twisting. And so the applications that I want to mention here is anything that's twisting. On or off. So a bottle cap. So you twist a bottle cap with the palm of your hand, and you twist it, and it goes upwards. The bottle cap comes up off the bottle. So also screws do this. There's more to it than that, but that just gives you a flavor for how can I be twisting something and it moves up or down, and there's lots of things that do that. Now, to find the size of U and V, which is this magnitude of U cross V, like this. So to actually find its size, so finding its direction, we'll use the right-hand rule, and that's a little awkward to get used to. But to find its size, we just use this formula. We go magnitude U, magnitude V, sine theta. In the applications part, we'll see why this is a great choice for finding the cross product. We'll see why this size choice is made. So if it's not clear why the sine theta should be involved here, it will become later in later lessons. Or it will become clearer in later lessons. But here the magnitude of U is 3, the magnitude of V is 8, and they said the angle between them is 30. So I've got 3 times 8 times sine 30. When I type that in, I get 12. That's the magnitude. You might be confused because you might have said, well, a few minutes ago you said that U cross V was a vector, and that is true. U cross V is a vector. But the size of that vector is 12. Its direction, we'd need to know more about U cross V, which I'll talk about in a second. Then V crossed with U. We go magnitude V, magnitude U, sine of the angle between them, and here I get 8 times 3 times sine of 30. And I found out something interesting about U cross V is that the magnitude of U cross V is the same as the magnitude of V cross U. The magnitudes are the same. However, what can we say about the directions of U cross V and V cross U? U cross V and V cross U are in opposite directions. So 2 notes about why that is. One, if you start your fingers on your right hand on a different vector, your thumb's got to flip over and got to head in the other direction. The other way to explain that is if you're twisting a bottle cap on or off, you'll twist it. If you twist it one way, it goes up. If you twist it the other way, it goes down. And that sort of gives you an impression of why we have this rule about, the right-hand rule about twisting here. And again, if you're having trouble picturing why U cross V and V cross U would be in opposite directions, that separate video should help with the visualization. Now, this is where it gets really interesting, and it sort of becomes simple for a moment, but there's a lot to show you. To investigate the cross product of algebraic vectors, first consider the unit vectors I, j, and k. So there's a nice little picture of I, j, and k with the definition of the cross product to determine the following products. Let's talk about I cross I. If you go I cross I, what you're going to get is magnitude I, sine theta. But what's the angle between I and itself? 0. So I'm going to end up with a sine of 0 in here, and so I cross I is 0. In fact, all of the time, every time you cross product something with itself, you get the 0 vector because the angle between the two vectors will be 0. And if you look at the formula for cross product, it's sine of theta, so when the angle is 0, you get nothing. Now, all the other vectors in the picture, I, j, and k, they all act at 90s, and I want you to write over here, a little note here, sine of 0 is 0, and sine of 90 is 1. So all of these I cross j, j cross I, k cross I, they're all going to be size 1. Let's just try and picture I cross j for a second. I cross j, if I put my fingers along I and move it towards j, really try to visualize that. That's really tough to visualize, but I can't wrap my fingers sort of in towards k. I've got to put my right hand fingers away from k, and when I wrap my fingers in towards j, my thumb's going to point upwards, and I'm going to get the vector k. See, it's going to be size 1, because sine of 90 is 1, and it's going to point straight up, which is exactly the k vector. Now, let's try, I'm going to jump ahead to j cross k over here. J cross k, if you put your fingers along j, you could actually put them right on the screen there, where they would, with your pinky right down on the screen, and you wrap your fingers towards k, your thumb's going to stick out towards I. In fact, every time you cross two vectors in alphabetical order, you'll get the other vector. And that's true here. Even I sort of call this alphabetical order here, k cross I, because it's going to the next one. K cross I, if you put your fingers straight up along k on your right hand and wrap them, they'll sort of wrap, the fingers will wrap straight towards your face. Your thumb will point along j. Now, what happens with the other ones, when you go I cross k, you'll find you'll get negative j. It'll come out in the negative direction. And j cross I is negative k. And k cross j is negative I. They always go the opposite direction when you're sort of going backwards. Why does that matter? Okay, separate PowerPoint to prove this. If you want to find the cross product of Cartesian vectors, which have to be 3D, by the way, you can't cross product 2D vectors because it would be the third vector would stick out of the plane and it wouldn't be a 2D vector anymore. Apparently, this is the formula for finding u cross v. u2v3 minus u3v2 is the first component. The second component is u3v1 minus u1v3. And the third component is u1v2 minus u2v1. Very, very strange here, but this PowerPoint proves it. Even though the proof isn't part of this course, you sort of have to see, get an impression with the proof to have some faith in this formula. Now, the separate PowerPoint here proves this, but also it does something important here, is that it establishes why I, j, and k are so important here. Like I, j, and k up to this point are just these cute little vectors, I, j, and k, but this is the first time that you're going to see why I, j, and k make some of the vector algebra so nice. So cross product of Cartesian vectors, separate PowerPoint, it's on the webpage. But again, you're not responsible for this proof. It's just nice to see it so that you can believe in that formula. So I've got two vectors. U equal u1, u2, u3, and v equal v1, v2, v3. And apparently, during this PowerPoint, I'm going to prove that to find the vector u cross v in 3D, it gives you this actually fairly simple formula to talk about this. Like it's going to exactly give the vector in the right direction and the right size, that is u cross v. Okay, well, we start with u cross v is u1, u2, u3, crossed with v1, v2, v3, and I immediately go to i's, j's, and k's. So I've got u1i plus u2j plus u3k as the first vector, and v1i plus v2j plus v3k as the second vector. And then apply the distributive law. Oh my goodness, what a mess I get out of there. You'll have to walk through each one. So you see u1i is crossed with all three vectors in the second vector, and then on the second bracket. And then u2j is crossed with all of the vectors in the second bracket. And then u3k. So all those that you're seeing right here, there, and there. There's the three vectors from the first set of brackets, and they're all cross product with everything in the second set of brackets. And when I distribute each of those, I get this giant mess, which looks like big trouble. Most people would stop here and go, well, that's it, I'm done, I'm out. And all they've done here is distributed, 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 and distributed. And if you're unhappy with that whole mess, me too. But take a look at each individual pair. Each individual pair has combinations of II, IJ, IK, JI, JJ, JK, KI, kj, and kk. And what happens is, when you multiply those each individually doing the cross product, you'll get just what I said, I cross I cross j, I cross k. But look at this one here became u1 v1 multiplied with I cross I. And this one here became, up here, u1 v2 with I cross j. So then I can do those individual cross products. And these individual cross products here are just the exact ones I was just showing on the other, in the word file over there, is that you're just cross producting two unit vectors. And if you do each one of those and map them through each specific time and evaluate them, you get all either zeros or a single unit vector. For instance, I cross I came out to 0. I cross j came out to k. I cross k came out to negative j. And I've just substituted each of those individual ones in there. And so life gets really simple, really fast. All the zeros disappear. And I'm left with u1 v2 with the k vector, u1 minus u1 v3 with the j vector, minus u2 v1 with the k vector, plus u2 v3 with the I vector. And it's starting to look like what the original proof said. If I just rearrange them with the I vectors and j vectors and k vectors, it's not long before I get exactly the proof. It is such a stunning, beautiful proof, and a great example of why I, j, and k are so valuable, because fairly easily, it wasn't completely insane. It's just distribution. And if it seemed completely insane, watch it again, because it really is not anything more than some distribution. And using what I was showing over here, which is that every pair of unit vectors either comes out to 0 or another unit vector. Okay, not responsible for all of that in this course. What you're responsible for is using this. Now, I'm going to show using that twice. Once, right as it sits there, just a straight plug-in, and then a shortcut. It'll remind you sort of like synthetic division, where there's a shortcut to doing this, or a better way to handle all the numbers involved here. But if I just put this right here, I can do u cross v with the formula sitting right there. And I'll be honest, I didn't really know the trick until much later. I always did the cross product exactly like you're going to see me do here, is I look at the formula and I go, okay, so they want u2, which is 5, times v3, which is 8, subtract u3, which is negative 3, times v2, which is 1. So I'm just actually plugging into the formula using, that first one's u1, then u2, and u3, and this vector is v1, v2, and v3. And then I go to the second component. The second component is u3, which is negative 3, times v1, which is negative 2, subtract u1, which is 1, times v3, which is 8. Wild to try and keep track of all that stuff while you're going here. But then u1, v2, which is 1 times 1, minus u2, which is 5, times v1, which is negative 2. After you've done all that, it's really easy to simplify these. And I get a 43, negative 6 minus, 6 minus 8 is negative 2. And then, let's see, 1 plus 10, I get 11. Unreal in both ways. Lots of numbers to keep track of, but unbelievable that this formula that easily comes up with the third vector here that is exactly perpendicular to the first two vectors and points in the exact direction indicated by the right-hand rule. A stunning result. That's really this lesson in a nutshell right there, is being able to do those cross products. So now all I'm going to show you is a short version of doing that. More refined, I'll call it. I'm going to do the exact same question another way. U vector is 1, 5, negative 3. V vector is negative 2, 1, 8. Find U cross V. Here's the shortened or more refined way to do it. Write the first vector, 1, 5, negative 3. But repeat the first component. Write it again as a 1 there. Then do the same thing with the second vector underneath. Negative 2, 1, 8, and rewrite the first one here. You'll see why I'm rewriting it in just a second. And then it's important to write the first vector that you're doing on the top and the second vector on the bottom, because u cross v is not the same as v cross u. So what I want you to do is picture 3 boxes. And so when I say picture 3 boxes, I'm going to show you what I mean by 3 boxes is when you go to do the first component, your box is there with the second and third component. When you go to do the second component, your box is here, which is actually the first and third component. And when you go to do the third component, your box is there, which is the first and second component. You may have to rewatch that part of the video to see those match up with the boxes I have right here. Now, you don't rewrite the boxes. You sit right here and you go, okay, when I'm doing first component, I just go 5 times 8, subtract negative 3 times 1. That's what I got right here. And then, are they going to let me erase that easily? Yeah. Then when I do this second component, I just go negative, I just do negative 3 times negative 2, subtract 1 times 8. And that's what this is showing here. It's just showing the individual work in those boxes. And then the last one, when I want to do the third component, I just go 1 times 1, subtract 5 times negative 2. So all the numbers are laying there. You're really just doing some cross multiplying there. That takes some getting used to. You're going to have to walk through that example yourself. Write all the numbers down and try and walk through each piece of that yourself to get used to how this is a more efficient way to do what you saw me do up there. That takes practice. I won't lie. You're going to have to sit down and map through one and play around with it until you go, oh, I got the answer, and then try another one. But it is a vital part of vector algebra, and so you really need to nail this thing down. So, from the beginning, if that all seems pretty wild to you and you want to see it all in action, here's one right from the beginning with all the instructions in there. So, I'm doing 2, negative 5, 4, cross product with 3, 1, 2. So I write down the first vector, 2, negative 5, and 4, but I repeat the first component there. Then the second vector, I go 3, 1, 2, but I repeat the first component there, which is a 3. So when I'm going after the first component, I use 2 and 3 here. So I go this, subtract this, those two cross multiples. So negative 5 times 2 is negative 10. Subtract the 4 times the 1, which is subtract 4. And then, got to erase those 2 lines there. When I go to do the second component, I use these two. 4 times 3 minus 2 times 2. Showing all the numbers that time. And then when I get back to the third component, then I want the first 2 parts this time. So 2 times 1 minus negative 5 times 3. So 2 times 1 minus negative 5 times 3. And I get negative 14, 8, and 2 plus 15, 17. That easily. That easily. Okay, not that easily when you first see it. You're confused while you're watching me do it. I totally get that. But you saw how fast I can do it, and it's not that complicated where you're getting these numbers from. It just takes practice. Next example. Find a vector that is perpendicular to 1, 2, 1 and 3, 0, 4. If I want a vector that's perpendicular to these two, let's just go back and remind ourselves what cross product is. The cross product of 2 vectors is the vector that acts perpendicular to both u and v. That's exactly what cross product does. It finds a vector perpendicular to the first 2. So if I want to find a vector perpendicular to these 2 vectors, all I got to do is find its cross product. So I'm just going to go 1, 2, 1, cross product with 3, 0, 4. Here comes the whole procedure again. Write the first vector out. 1, 2, 1, rewrite the first component. Write the second vector, 3, 0, 4. Rewrite the first component. And then, if I want to find the cross product, to do the first one, there's the cross multiples, 8 minus 1. To do the second component, there's the cross multiples, the next one in line, 3 minus 4. And due to the third one, I go back to 1 and 2 again, 1 times 0 minus 3 times 2 is 6, and I get 7, negative 1, negative 6. I made a mistake there. That wasn't an 8 minus 1. It was an 8 minus 0, so that's an 8. 8, negative 1, negative 6. That's one vector that would work. That's a cross product of there. And this is verify that that's correct. Well, how are we going to verify that this is perpendicular to those two vectors? Because it's virtually impossible to picture. But we do have a weapon. We have a weapon from 2 days ago. The dot product is exactly what's needed to test to see if something's perpendicular. That is, what I'm going to do is take the original vector 1, 2, 1, and I'm going to dot it with 8, negative 1, negative 6. And what I get here, if you don't see where I'm going with this, watch what happens. I get 8 minus 2 minus 8 equals 0. Therefore, perpendicular. I'll test the other vector too. 3, 0, 4, dotted with 8, negative 1, negative 6. I get 24 minus 24. I get 0. Therefore, perpendicular. It's perfect. The cross product creates perpendicular vectors. The dot product tests to see if vectors are perpendicular. Were there other possible solutions here? Yes. Any collinear vector with 8, negative 1, negative 6 will work. So any scalar multiple of it. I could multiply it by anything I wanted. Notes about cross product. The cross product is a vector and is sometimes called vector product as opposed to dot product, which is sometimes called scalar product. The cross product is only defined in 3 space. Why? Well, the third vector is always going to stick out of the plane of the first two because it's going to be perpendicular to the first two. So your third vector is always going to stick out of the plane, immediately making a 3D vector. So you can't just do this in 2D. When calculating the product of the vectors, order matters. U cross V is not the same as V cross U. They act in opposite directions. And note the use of this little cross and this little dot. You've seen that cross before as the regular multiply symbol. We use that to represent cross product. When we want to do dot product, we actually use a dot to represent that in vectors. The following vectors can be proven using algebra, but we don't prove them here. We just want you to know them. U cross V is the negative of V cross U. You can distribute with cross product. You can distribute with scalars and cross product. And if you cross product something with itself, you get the 0 vectors. Many of those came up in the middle of all this lesson. Okay. Coplanar vectors. So, a big idea here. Recall that U cross V gives a vector that is perpendicular to the two vectors being multiplied. So that means that we also know that if we have two vectors and we dot them to get 0, then the vectors are perpendicular. How can we use these properties to decide if 3 vectors are coplanar? Well, here's the idea. If you make a vector by doing U cross V, you're going to get a vector that sticks out of the plane of those two vectors. It's not going to be coplanar. It's going to stick out of the plane. If you then take that vector and dot it with a third vector that you're curious about, it should come out to be 0 if it's going to be coplanar. It should be perpendicular. So what we say is, if U cross V dotted with some W comes out to 0, then we know they're all in the same plane. So we've got this U cross V, we've got this vector sticking out of the plane. If the third vector is in the same plane as U and V, when you dot it with your thing that's perpendicular to U and V, you're going to get 0. And then the test also says, well, if U cross V dotted with W is not 0, then they're not coplanar. Let's just go over it again. Let's say I've got 2 vectors in a plane, and the plane being the screen you're looking at here, U cross V, or U and V. If I've got U cross V, I want you to picture if U cross V is sticking right out of the screen at you, coming straight up at you. if I've now got a third vector, w, and if that w is in the plane, it's going to be perpendicular to the vector u cross v, which is sticking straight out of your screen. If it's not perpendicular to that, w is not in the plane, which means they're not coplanar. So this u cross v dot w has a special name called the triple scalar product, or the scalar triple product. And we don't need brackets here because the only way this can be done is to do the u cross v first, because you need a vector to be dotted with this vector here. What I mean by that is you can't do the dot product first, because you'd get a scalar and then you can't cross product it. So, last chapter we did determine if three vectors are coplanar. And it was really quite a procedure. We went, okay, if they're going to be coplanar, we went, oh, w's got to be equal to au plus bv, and it was a whole page of algebra to make that decision. Apparently, this is all we got to do. We got to go u cross v and dot it with w and see what happens. And if this explanation was only so-so up here, I'll try and explain it a little more as I'm doing this example. First, I'm going to go a cross b. So, 1, 1, negative 2, 1, 2, negative 3, 1, repeat. So now I'm going to do it without the lines on there. There's the pair. 1 minus 6 is the first component there. Then the second component would be those two. And I get negative 4 minus 1. Then the third component would be back to the first two now. I get negative 3 minus 2. So what I get is negative 5, negative 5, negative 5. There's the vector that's perpendicular. That's the one that, whatever the AB is, whatever plane they create, whatever plane they're in, this vector sticking straight out of that plane. Okay, now let's just test that a cross b with c. So I've got my a cross b. I'm going to test it with the c. That is, I'm going to take this a cross b I found, negative 5, and dot it with the c vector now. And what I get is 5 plus 10 minus 15. I get 0. What does that mean? It means the vector that was sticking straight out of the plane of A and B is perpendicular to the C vector. And the only way that can happen is C's got to be in that same plane. C's in that same plane as the other two vectors, and therefore A, B, and C are coplanar. Okay, if that's confusing, let's do it all again. What I'm going to do is I'm going to first find this vector, u cross v. And this vector will stick straight out of the plane that has u and v in it. So u cross v. I'm going to do the work down here. 1, negative 1, negative 1, repeat the 1. 2, 1, 4, repeat the 2. Negative 4 plus 1. Negative 2 minus 4. And then 1 plus 2. And I did that one a little faster on purpose to motivate you that with a little practice, that procedure can go pretty quickly. Now, so u cross v is this vector that sticks straight out of the plane that has u and v in it. Now I'm going to test it with the w. I'm going to go u cross v dotted with w. And u cross v was negative 3, negative 6, 3. And w was negative 1, negative 1, negative 1. And what I get is 3 plus 6 minus 3. I get the number 6. What does that mean? All it means is that the vector w is not perpendicular to a vector that sticks right out of the uv plane. So it can't be in the plane. If it was in the plane, it would be perpendicular. Therefore, u, v, w are not coplanar. that W isn't perfectly aligned with U and V in such a way that it's perpendicular to the UV cross product. I will not pretend for a moment that whole idea is easy. But the big thing for now is knowing these two qualifications. And as we work through it, hopefully the rest of it will become clearer. Okay, I gotta say, these are a little tricky, these type of questions, these examples here. And I just want to say, when we use a dot and there's vectors involved, we mean vector dot product, nothing else. You can't substitute and change in the middle and decide that dot means something else. And when we're doing vectors and we use this, we mean vector cross product. Only. No resubstituting for old numbers and so on, like that, old operations. When we're doing vectors, those two things mean that. So this says state whether the following expressions are vectors, scalars, or meaningless. Well, this says we've got A, which is a vector, and they want to dot this with B cross C, which is also a vector. And if we dot two vectors together, we're going to get a scalar. When you cross product two vectors, you get a vector. And so the B cross V is a vector. Then there's a dot there telling you, oh, dot these two vectors. Vector dotted with vector gives a scalar. Dot product results in a scalar. Let's try another one. First bracket is A dot B. So the two vectors dot product together, we will get, a scalar. And they're asking us to cross product that with another scalar. And that's not possible. You can't take a scalar and cross product it with another scalar. That's not a thing. You say, oh, well, that means multiply. I could just switch to multiply. No. When we're doing vectors, those symbols mean exactly what we write. They mean dot product and cross product. This one, vector crossed with, well, B cross C will be a vector. And when I cross product a vector with a vector, I get another vector. Last question, can we use the cross product to determine if two vectors are collinear? And the answer is yes. If U cross V equals 0, the vectors are collinear. Only an angle of 0 degrees or 180 degrees will give U cross V equals 0. Now listen, if you don't have a headache at the end of that lesson, you probably weren't watching carefully enough. That lesson has some trouble to it. And some of it you have to just do some of the homework and get used to the algebra so that's not what's holding you up. Get the algebra nailed down and get the numbers nailed down and let the ideas sort of work their way through. I'll try and include a couple of videos that help with the visualization of things that have gone on here. So check those extra videos out that I've posted.